Thank you. Thank you for the introduction. And my name is Hengky Chandrahalim. I'm speaking on behalf of the first author here, Jeremiah Williams, who is unfortunately unable to attend this conference. And the title of our talk is Harnessing the Fourth Dimension Through Nonlinear Damping in Optical Fiber Flow Sensing. So this is the motivation behind this work. We would like to reduce the size, weight, power, cost of microsensors, especially those related to applications in aerospace that you can see in here. We have small drones, and they are unable to carry like bulky sensing components. So we would like to reduce the size of the sensors. We also would like to reduce the packaging requirement as well as while keeping the high performance of the sensors. And we would like to integrate the sensing elements with low loss and media that have immunity to interference. And finally, we would like to explore advanced microsensors fabrication and integration techniques. So the device design is shown in here. It has a lateral dimension of about 110 micron. We do need to have this pedestal here to promote adhesion to the tip of the fiber. The diameter of the fiber here is 125 microns. And the sensor has 3 microplates here that rotates in response to incident airflow. So when the light is shined through the core of the fiber, it will be reflected as the blade pass by the cores. And there is a stator that is shown in here that holds the fiber. And we would like also to reduce the friction between the bottom of the fiber and this. So we have this friction reducing feature as shown in here. So because we use two-photon polymerization to create this device, so we need some support that is shown by this support here to support the blades during the fabrication. And it is also important to note that because we need to deposit a reflective material underneath this microplates, so we have this masking brick here to help to protect the core of the fiber during the deposition. So we use two-photon polymerization to create the device, which means we solidify the volume of photosensitive resin to create the 3D structures that we need. Now we can use a single UV photon to polymerize photosensitive resin, but as you can see or illustrated here, that the size is of the reaction volume is very large. Now when we use 2 photons and 2 photons with lower energies are absorbed simultaneously, then that reaction has to happen in a very, very small volume there. That can be in the order of less than 200 nanometer. So this is just to highlight the fabrication of the device. We first prepare the fiber tip, cleave the fiber, clean it using alcohol, and put the resin, photosensitive resin. We use the commercially available nanoscribe professional GT to create this 2-photon polymerization. And the polymerization itself happens for about 5 minutes. And on the right here, you can see different stage of polymerization, and this is the device when it is done. It still has all the supports that supports the microplates. So we use the PGMA solution to develop the resin and remove the unwanted resin. And after that, we rinse that in the IPA for 10 minutes. So what is shown here is the colorized LCM of the device after it is done. You still see the support colored in orange here, and the mask that protect the core is that little brick shown in blue here. So first, we need to use the probe tip to remove the these supports that is shown in here. And after that, we sputter a reflective material to have a reflective film underneath the plate, so that helps to reflect the light that comes from the fiber. And then at the end, we remove the little cube that helps to protect the core. The experimental setup is shown in here. We use the nitrogen to introduce the flow to the device. The device itself is mounted to the fiber chuck, and we use also the mirror mount to hold this fiber chuck. And for the light source, we use the broadband illumination diode that is connected to the optical circulator. And then the light is transmitted to the device through the port 2 of the optical circulator here. And then the reflection is captured by the optical power meter that goes to the oscilloscope. The next slide shows the video of the working device. Hopefully this works. Yeah, so that's just to show that the device works and that rotates. The microblade rotates. So here you can see the two examples of the detected flow. Each peaks that you see in here, that corresponds to the reflected light. Now, as you can see here, that we don't have like a uniformly spaced peaks as we expect to have if we want to characterize a good flow. So we did a fluid dynamic simulation, and we found that the dynamic at the fiber tip itself is very complex. There are turbulence and different pressure on the plates as they pass over the fiber, and that causing like a wobbling and inconsistency. And besides, like the gap between the stator and the rotor also introduced a friction that caused also instability and wobbling. Now, in order to address this issue, we need to study some damping agents that can be applied to solve this issue. So the requirement is obviously low toxicity and good thermal stability, as well as hydrophobic, because the damping agent needs to get into the gap between the stator and the rotor, which is about 2 microns. So, and we found this polydimethyl siloxane hydrocarbon damping agent is a suitable one to use. So we applied this damping agent to the structure after it is released, and we dry it, and then we do a series of experiments, flow sensing experiments. Now, as you can see here, if we compare the performance of the device with and without stabilizing agent or damping agent, on the left, shown in orange here, are the measurement without the damping agent, and we can see a very sporadic response, while on the right here, plotted in blue, once we apply the stabilizing agent, we have like a uniform peaks that we can characterize. And we can also sense like a broader range of flow. So the next step, we can even do the fast Fourier transform and do like a frequency study from there, and we can clearly identify the frequency components that corresponds to our previous measurements. When we plot the frequency as a function of the flow rate, we can see this nonlinear behavior, and our conclusion so far is because the damping agent itself is nonlinear, as well as the friction itself is also nonlinear, so we have this kind of response. However, this kind of response can be modeled, and we can optimize a certain region of the flow rate for a better sensing performance. Now, to conclude, so we have demonstrated the 3D optomechanical flow sensor on optical fiber tip. And nonlinear damping was successfully introduced to stabilize the flow. And we have also demonstrated the two-photon polymerization that can miniaturize flow sensing elements on the tip of the fiber. We still need to do a further study to incorporate ferrule and housing to improve the survivability of the device. And we also would like to do experiments to demonstrate flow sensing in other different media. That concludes the presentation today, and I'll be happy to answer any questions that you may have.